In this segment, we'll continue looking at electricity in photovoltaics by learning how to measure some of the key electrical parameters, voltage and current. These two values are important because the voltage multiplied by the current equals the power, and we're always looking at power to evaluate system function and performance. Jumping right in, voltage, which is the system potential, needs to be measured outside the circuit. We do that using a voltmeter. A voltmeter essentially has infinite resistance, so no current flows through it. Current, which is the other measurement, is measured in line, so electricity will actually flow through the meter. This can be potentially unsafe or difficult to do in practice. So the other way to measure current is to use a clamp-on meter, which measures the electromagnetic field generated by moving electrons, and then just converts that value to a current. In practice, a clamp-on meter is almost always used since it's much safer and easier. Remembering that once we have the voltage and the current, we can multiply them together to get the power output of the individual module or the array. We can subject a module to standard test conditions and measure the voltage and current generated by the cell. The product of those two is the power, or watts. Because this is done under standard test conditions, it also equates to the nameplate rating of the module or the array. So how can we measure current and voltage within the cell or module? Well, voltage is essentially constant because it's defined by the material itself. However, it does vary somewhat with temperature, something that we'll look at in a future module. Current, however, scales linearly with brightness. While it too has some slight variations with temperature, higher radiance means more photons, and more photons means more electron movement, so current increases with brightness. By knowing voltage and current values under certain conditions, we can define both the power and the performance of the cell. One important value is something called the open circuit voltage, or VOC, which is the highest voltage that can be generated by the cell. Physically, this only occurs when there is no current flowing through the system. In everyday life, it's equivalent to having a battery that's not connected to anything. There is a potential or push between the two poles of the battery, but there's no current flow. The other important value is the short circuit current, or ISC, which is the highest current output by the cell. This equates to the flow of electrons when there is no resistance in the circuit. This would be the electrical equivalent to putting a wire with no load or resistance between the two poles of the battery. Needless to say, don't do this. But the VOC and the ISC are two extremes for voltage and current, and these are typically placed on a graph with voltage on the x-axis and current on the y-axis, and that is known as an IV curve. By increasing the load on the cell through increasing resistance, a cell will move from the ISC point to the VOC point, generating this curve. Adding resistance is the only way power can be extracted from the cell. In reality, this is the role of the battery or the inverter. Recalling that voltage multiplied by current equals power, at some point along this curve there's a point of maximum power, known as the maximum power point. It's symbolized as Pmax or MPP. The power is 0 at ISC because the voltage is 0, and the power is 0 at VOC because the current is 0. The maximum power point is going to be the furthest point from the graph origin, and the voltage at that point is defined as VMP, or voltage at maximum power. And the current is defined as IMP, or current at maximum power. In reality, we can continuously add resistance and measure the current and voltage and calculate the power at each point, with the largest product being the maximum power point. Well, why does this work? The photovoltaic follows one of the fundamental laws of electricity, Ohm's law, which states that voltage is equal to the current multiplied by the resistance, or V equals IR. Mathematically, when the resistance is 0, the voltage must also be 0. This is because there's no potential difference between the electrical signal and ground. Likewise, when the resistance is infinitely large, the current is also 0 because no electrons can flow through the circuit. This matches what we observe in reality as well. This IV curve is used to help us evaluate individual solar cell performance using a term called fill factor. The fill factor is a ratio of the measured power to the maximum possible power. The measured power is the voltage times the current at maximum power. The short circuit current, ISC, multiplied by the open circuit voltage, VOC, yields the highest theoretical power. And the ratio of the actual maximum power, the theoretical maximum, represents the performance quality of the cell because it shows losses from internal resistance of the cell. An ideal solar cell would have the same current as resistance increases and then drop to zero at VOC. In reality, the fill factors for solar cells tend to be around 70 to 80%, and that fill factor decreases slightly over time due to degradation of the conductors or other materials within the cell. While the fill factor is not typically reported for photovoltaic modules, it's the physical manifestation of the cell efficiency, since it defines how good that cell is at converting photon energy to electrical energy and putting it through a circuit. So let's now look at how to use these important values, VOC, ISC, VMP, IMP, and Pmax, to calculate fill factor. So in this case, I'm using a generic specification sheet where the short circuit current, or ISC, is 8.2 amps, the open circuit voltage is 37.1 volts, the maximum power current is 7.7 amps, and the maximum power voltage is 30.1 volts. Well, if I multiply the open circuit voltage by the short circuit current, the product is 304 watts. So the power at the top of that corner of the orange square is 304 watts. Likewise, if I multiply the maximum power current by the maximum power voltage, I get 232 watts, which is actually the power rating on the panel. That is where the point is of the blue square. Now, if I divide the 232 watts, which is the maximum power of the cell, by the 304 watts, which is the theoretical maximum of the short circuit current multiplied by the open circuit voltage, I get a ratio, or a fill factor, of 0.76, or 76%. Now that we've looked at how to measure these values and perform the calculations, in the next segment we'll look at how to calculate photovoltaic system efficiency and power from that system, as well as look at the components of a photovoltaic circuit from sunlight through to the external system.